In last video, we looked at linear regression. In this video, we shall talk about logistic regression. So, unlike its name, logistic regression is a classification algorithm. It is a classification algorithm. So, what happens in a classification algorithm? It will have discrete, actually it's T, right? Discrete value outputs. Now, what do I mean by that? These are called classes. So, either there will be two classes or there will be multiple classes. It is called logistic regression because it uses linear regression behind the scenes. So that's why it is called logistic regression. But I'll talk about that too. So if you have two classes, two output classes, we'll say it is binary classification problem. And if we have multiple classes, we'll say it is multi-class classification problem. Multi-class. All right. So let me give examples. So suppose if I have to tell an email is spam or not spam, this will be a binary classification problem because either the spam will be either the email will be a spam or it will not be a spam. So that's why it is a binary classification problem. Whereas if I have a problem like this, I am given with an image. Okay, I have to tell this is image of an animal, and I have to tell my model has to predict it is a dog, it is a cat, or something like monkey, or other animal like zebra. So there are multiple outputs. Okay, so in such problems we say these are multi-class classification problems because we have multiple classes like there's dog, cat, monkey, zebras. But whereas in this one we have only two classes, either it will be spam or it will not be spam. So this is a binary classification problem. So let's talk how it is going to use linear regression because it is very important to understand maths behind it, right? So see what happened in linear regression. We were getting a line which was y hat equal to mx plus c, but in logistic regression we have a bit different because we have only two classes, right? We are talking about binary classification. So let's take example of cancer prediction. So we do have cancer cells, right? uh, we will have two outputs. For one, we will say it is malignant. For zero, we will say it is benign. Benign is less riskier one. So we have cancer cells, right? But when they exceed certain size, they start getting malignant. They start getting malignant. So what will happen? On x-axis, I'll say this is size of that cell, and on y, I'll have two outputs, 1 and 0. Okay, 0 is this one, and I'll have this line. And my data, it would look something like this. It would look something like this. And after a certain size, the cancer cells start getting malignant. Okay, 1 means they are malignant, 0 means they are benign. Fair enough. So 1 means they are malignant and 0 means they are benign. Okay, so one way to solve this problem is I'll fit a linear regression model to make a linear separable boundary like this, and this line will be x equal to 3. See, slope of this line will be infinity. Okay, I hope you know this much of maths, but if you don't, then just assume what I am saying. Slope of this line would be infinity. But what happens in linear regression? Okay, in linear regression we are having continuous value outputs. Okay, in linear regression we are having continuous value outputs. Okay, so what will happen for every point? For every point it will predict a line, predict something on this line. Okay, for every point it will predict y over this line, but we do not want that. We want only two classes, right? And furthermore, the another issue, if suppose I have a data point like here, okay, and this should be classified as malignant, but what linear regression will do, it will see, okay, I have new data point, so let's fit it more better. Because what we do in linear regression, we fit it like this, right? We do mean squared error of this distance between the points and the predicted points, because the point that will be predicted for this point would be something like here. Okay, suppose I have a point here. What I'll do, I'll just predict it here, then I'll try to minimize this distance, right, in linear regression. But I do not want that thing right now, because I'm not doing that. I'm doing classification. I have to classify either it is malignant or it is benign. So what I'll do, uh, there's a function there's a function, we call it sigmoid function. Sigmoid function. See, still now we are talking about what? Binary classification. We are talking about binary classification. So this sigmoid function comes really handy, because sigmoid for z would be 1 upon 1 plus e raised to power minus z. Okay, and this function makes a continuous value to look like what I'll show you in a few while. See, suppose z is a continuous value, so sigmoid of z would look like, okay, this is 1, this is 0 0.5, and here is 0. Okay, sigmoid of z would look like this. So it will shrink down the continuous value into the range of 0 to 1. And we also know this is range of probability, right? So one thing that I can do is use linear regression to fit this line, actually just to make this line, okay, not fit it, okay, and just remove this MSE square loss, because we do not want that here. I'm just using linear regression to just get this line, okay. And then what I'll do, I'll pass this continuous value predicted by my linear regression model into sigmoid. Now, what sigmoid will do, sigmoid will give me a value within range of 0 to 1. Like linear regression will give me values here also, here also, here also, here also. So it is a continuous range of values, right? But sigmoid will shrink down these values from 0 to 1. Now, what I can do is simplify it further bit. I'll say, I'll say, see, what linear regression did, it gave me a continuous value. Okay, sigmoid shrink it down from 0 to 1. Okay, yet these values are continuous in range of 0 to 1. Now what I'll do one simple thing. If this y hat, now see, these predicted values are y hat, okay, these are the predicted values of model. What we did, we just used this y hat to get this y hat, which is from 0 to 1. Now what I'll do, this y hat is greater than or equal to 0 0.5. I'll say it is what? I'll say y hat is 1 now. Simple. Else it is 0. Y hat equal to 0. So what I'll do, see, for suppose I have a point like this, okay, size of the cell is somewhere out here. What linear regression will do, linear regression will predict it here. Now what sigmoid will do, sigmoid will bring it from 0 to 1. It will bring from 0 to 1. And now suppose sigmoid predicted it here, okay, this is courtesy of sigmoid function. Now what I'll do, I have that if else condition. It said, if it is greater than 0 0.5, just make it 1. Okay, so I brought this point here. Okay, make it a bit clear. Okay, this is 1. Let's say this is 0 0.5 and this is 0. Okay, suppose and this is my line. Okay, this is the linear regression line. Okay, let's say I have a point here. I have a point here. Okay, what linear regression will do? Linear regression will predict it here. Okay, this is prediction made by what? Linear regression. Now what sigmoid will do? Sigmoid will shrink it down to the range of 0 to 1. Let's say my sigmoid brought it here. Okay, this is same prediction y hat but using sigmoid. Okay, sigmoid brought it down from 0 to 1. Now what I'll do, I'll come to this if else statement which I wrote here. I'll come here, I'll see this point after I got from sigmoid is actually lesser than 0.5. So what I'll do, I'll say this point is actually benign. So I'll do this. So this was just an example, but when this model will work, it will actually give me somewhere here. So this is actually negative prediction because I'm getting false, because I know that this point will be a malignant cell, but I'm getting benign. So how will I manage that? So for that, again, we have something like loss function. So let's talk about loss. Okay. So for loss of logistic regression, I'll just say it is very simple, but have some uh, I would suggest just listen to this closely. So for loss, I'll have just two conditions. So see, cost if y is 1. If y is 1, what I'll do, my cost will be minus of log of y hat. Okay, I'll explain it later, but again, there will be another thing. Cost if y is 0, then it will be negative of log of 1 minus y hat. Okay, so let me make something clear first. See this y, okay, this y is actual value and this y hat is predicted. Okay, same for this y and this y hat. Okay, now let me tell you how this is happening. So we'll have like four cases. Okay, cases. So there will be case 1, there will be case 2, there will be case 3, there will be case 4. Okay, and just make it like this. Okay, I have four cases. Now what I am saying, see, we'll have only two classes, right? This is binary classification problem, so I the output will be either 0 or it will be 1. Okay, because of that if else part that we wrote earlier, so it will be either 0 or it will be 1. Okay, so now see, let's come to case first. Case 1 is when I have actual value is 0 and I am getting 0 2. Okay, so y hat is 0 2. Okay, this y equal to 0 is here and I am getting also 0. So what I'll do, I'll use this, so negative of log of 1 minus 0, that is nothing else than log of 1, and log of 1 is 0, so this will be 0 because what I wanted I'm getting it, so loss is 0. I do not want anything else. Okay, loss is 0 is in this case. Second case would be y equal to 1. Okay, the actual value is 1 and what I am getting is also 1, so my prediction is also 1. I am getting a correct prediction, that is 1. So in this case I'll use this formula, negative of log of what? Y hat, so that is 1, and again log of 1 is 0, so I'm getting 0 because of what I wanted I'm getting it, so loss is 0. Simple. Now third case would be when y was 0 but y hat was 1. I'm getting opposite prediction. In this case, again, I will come back to this formula. I'll say log of what? 1 minus y hat. But y hat is 1. So I'm getting this. So this is negative of log of What? 0. Now log of 0 is negative of infinity. Negative to negative, this will become positive of infinity. So I'm getting an infinitely big loss. Okay. So for this, I'm getting really high penalty. I'm getting really high penalty. But I want that because I want to minimize my loss. And this is a false prediction, so I want to minimize it. I want this lesser than uh, I want it much less as it can be, so I will say take high penalty for that and that minimize it. Okay, so I'm getting high penalty for wrong prediction. And then again, fourth case would be when y was 1 but I got y hat equal to 0. Again, this is negative prediction because I am want the actual thing that I want, like it was a malignant cell but I got benign, same as the one we saw in example. For that we also want to charge high penalty. So what I'll do, I'll use again that formula of negative of log of y hat, that is 0. And for that again I will get very high penalty, that will be what? Positive of infinity. Now I have to minimize this loss. Okay, so my overall cost function would look something like this. J equal to, it will be mean of squares of all, mean of sum of all losses. Sorry, mean is actually sum divided, it is average, right? So it will be mean of all losses. So 1 upon n, and where n are number of samples. These are the data points that I have. Okay, so it will be sum of I equal to 1 to n and then this loss. And again, if you want to simplify it further, we'll write it like 1 upon n, I equal to 1 to n. Then what I'll do, see, simple, yi. Okay, see, uh, this whole thing, I can write as, I can write as, this whole thing I can write as y negative of y log y hat. Okay, minus 1 minus y hat, sorry, y, this y is actual output and y hat is predicted output, that's why log of 1 minus y hat, right? So if you don't get it, see what's happening is when I'll have y as 0, in that case this whole term will become 0 because multiplying something by 0 is going to give me 0, and this will become 1 minus 0. This will become 1 minus 0, that is 1, and if you multiply something with 1 it is going to get 1, right? And then this log of 1 minus y is nothing else than this minus, right? So this is same thing, and if I have y equal to 1, in that case this 1 minus 1, this term is going to get 0, right? 1 minus 1 is 0, then you multiply this term with this term and this portion is going to get 0, and then this is 1, so this will become negative of log of y hat, and this is similar as this one, this is similar as this one. Okay, clear? Now what I have to do here, I'll say negative of yi, okay, log of y hat I, right? And then negative 1 minus yi log 1 minus y hat I. So, so this is the entire cost function. So I have to minimize this thing, okay? Whenever I'll do wrong prediction, it is going to give me very high penalty. And for right prediction, it is going to cost me nothing, right? So this is how linear regression works. And again, we can use gradient descent again to optimize it. We can use regularization as well, but right now we do not want that because we'll look at that in further topics. I mean further videos. And see, another thing that I would like to mention, uh, it is not always the case that you have a linearly separable boundary. Like till now we have points like this, right? We had points like this, and suppose different points were on this side, and we got a linearly separable boundary. Okay, this is linearly separable. But in some cases, like see, I'm taking a very simple example. In real life you are never going to get it, but if we have something like this, we have unit circle, right? This is negative of 1, this is 1 1 1. Okay, sorry, this is 0 comma negative of 1, this is 1 comma 0, this is 1 comma, this is 0 comma 1, and this is 1 negative 1 comma 0. So we have a unit circle like this, and what we do, we have to predict something like inside this circle, inside this region, we have y equal to 1. Okay, prediction is 1, and for here we have y equal to 0. Okay, let's say this is x-axis, this is z-axis. Okay, just for our simplicity. So what we will do in this case, what we will do in this case, uh, linear regression is not going to give us this y hat equal to mx plus c. We can use multivariate linear regression, but we will need the equation of a circle for that. So we know equation of circle is like, so what is equation of circle? It is actually r square equal to x minus h square, right, plus y minus k square. Do you recall this equation? Okay, let me tell you again. See, suppose this is x, this is y, and I have circle like this. Okay, this center of the circle, the center of the circle will be h comma k, right? And this is r. So at any point, at any point in this circle, at any point in this circle, I will have hypotenuse as r, right? And then this. Okay, so let's say this point is x comma 0, and this point is uh, 0 comma y, right? So this triangle would be, sorry, this is actually a right angle triangle. So this triangle is something like this. So this region is actually x minus h, and this is what, y minus k, right? Because this point here was h comma k, which was center of circle. So this radius is actually, using the Pythagoras theorem, we are getting this particular thing. Okay, this is very basic thing. So for this, our unit circle example, where we had this unit circle, what we'll do, uh, for unit circle, let's say this color, for unit circle we can say, see, this center, this center is what, 0 comma 0. So putting that everything in that line, we can say, see, radius is 1, right? Radius is 1, r square equal to x square minus uh, x square minus h square plus y minus k square, sorry, y minus k whole square. So what I'll do, x minus k will become, see, what is x square plus y square. This is equation of a unit circle, and I'll just use it. Okay, and for this I'll just say if this is greater than equal to, see, again passing it to the sigmoid function and the predicted value. See, after this, using this line for multivariate linear regression, I'll just give it to sigmoid. I'll get I'll get 0 to 1 range, right? I'll get something like that. Then I'll use that if else. Okay, then I'll use if else, and I will get something like this. and then again using the same cost function and other things, I will be able to predict this point. If you don't get it, we'll have a programming implementation of this thing too. But if you don't get it, you should, I will suggest that you watch this video once again. I hope that you will get it. If you don't, you can comment down below. And thank you. That's all for this video. Bye bye. Take care.